Welcome back to another day of Math 210, Calculus 1. And today we're going to be talking about the fundamental theorem of calculus, at least the first part of it. And so this is really the capstone achievement of the full calculus course. What it does is it relates our two topics of integration and differentiation together in a way that's really, kind of natural, but also really interesting and beautiful. And I'll give you the formula. I'll sort of show you why it's true, and we'll do examples. But let's try to develop a little bit of intuition. Let's try to actually gain some insight into what this theorem is saying, and help you understand how someone might have discovered this in the first place. So if you go back to one of our original motivations, it was, we were talking about linear motion, so motion in a straight line, where you might have a function that tells you your position on the x-axis at time t. You would then take the derivative of that and get your velocity function. And the question that you might ask is, on some time interval from A to B, like what is your displacement? So like how far did you travel? Or if you were traveling forward and then backwards for a little bit, then it may not be your total distance traveled, but it'll be how much you were displaced from time A to time B. So like the question is, what is my displacement after traveling with velocity v? With velocity v on some time interval from A to B. So maybe A was like 1 o'clock and B is 2 o'clock. And so what's your displacement after traveling in your car for an hour at some varying velocity? And I'll just use like a very simple velocity function to show my example, like maybe v of t equal to t. And so here's the graph. It's just this straight line. And you have some beginning time, which you're calling A, and some ending time, which you're calling B. And we argued before that if your velocity was constant, then your distance traveled, which would be the displacement in this case, is equal to your constant velocity times the amount of time that you were traveling at that velocity. And we used that to kind of partition A to B into these subintervals, and we used that to realize that the total distance traveled is actually this area under the curve. And this is all for positive velocity, but if the velocity went negative for a while, then your displacement would of course be the distance that you traveled in the forward direction minus the distance you traveled in the negative direction. So like more generally, your displacement would be the signed area under the curve. But there's another really common sense interpretation of your distance traveled. So A is like your distance traveled. And on the one hand, this distance, as we've seen, is given by the integral from A to B of of the velocity, which is just t, but I'll write it as velocity. Which is just the area of this trapezoid. And you know formula for area of a trapezoid, it's the average of the two heights times the base, and so that's going to work out to b squared over 2 minus a squared over 2. You could also get that by the fact that the full triangle is b squared over 2, and you're subtracting off this smaller triangle. But there's another way to calculate your distance traveled that's really common sense. And this is the way that you might define displacement in the first place. And that's to say, if I just look at my position, if I look at where I ended up minus where I started, that should be the displacement. That makes total sense, right? Your position, so not your velocity. This is a graph of velocity. And if I instead look at my position, look at where I ended up minus where I started from, then that's going to be my displacement. And we know that the derivative of position is velocity. In our new language from Monday, that means that position is an antiderivative of velocity. And what does that mean? Well, also from Monday, we learned that all antiderivatives of t would have to be t squared over 2, perhaps plus a constant. And the fact that this goes through 0, perhaps plus a constant. Yeah, I guess we don't know what the constant is. So your position, whatever it is t squared over 2 plus perhaps a constant that tells you where you initially started out. That's not clear from our velocity. So it could be anything, whatever, but that's what we know about the position function, and we know it has to be an antiderivative of that velocity function, whatever it is. And if you just calculate P of B minus P of A, what you will get is simply B squared over 2 plus C minus A squared over 2 plus C. So whatever that constant was, we don't need to know it. It actually drops out of the calculation there. And we just end up with B squared over 2 minus A squared over 2. So two different ways to calculate the same thing. One was taking the signed area under the curve to calculate the displacement, and the other was just the difference of the antiderivative, that is to say, the difference in position. And you might start to think that, like, why is this true? Is this true because I happened to use the velocity function, v of t equals t? What if I used a different velocity function, like v of t equals sine t? Like, would it still be true then? And you start to think to yourself, yeah, of course it would still be true then, because displacement is always just the difference between your final and initial position. And the displacement, on the other hand, is always the area under the curve. It stands to reason that that formula is probably always going to work out. And so you might start trying to simplify your calculations. You might start saying, well, seems like it's true that any integral of velocity I can just calculate by evaluating the antiderivative, the position at the endpoints. And this is called the fundamental theorem of calculus. And in fact, it's true. universally. It doesn't matter if you think of your function as velocity, if you think of your antiderivative as position, this statement will be true no matter what for any function, so long as the derivative of this one is equal to that one. So to state it more formally, you could say that, say you have an antiderivative, like capital F prime of x is equal to little f of x, like, so you've got an antiderivative. Thank you. Have a good weekend. And let's say this, we want to be able to integrate this function without any problems, remove technical difficulties. Let's say that f of x is continuous. And mathematicians have worked over the years to actually weaken these assumptions, but that's not what I'm going to discuss today. Then it's going to be true that the integral from a to b of f of x dx is actually equal to capital F of b minus capital F of a. And by the way, we notate that by writing capital F of x with a vertical line and then the 2 points a and b. So we're saying that we are like evaluating this at the endpoints of the interval. So this explains the notation, this explains why we used this notation for indefinite integrals. We use that notation because you can use indefinite integrals to calculate definite integrals. And so this is called the fundamental theorem of calculus. Fundamental theorem of calculus, part 1. So it's really well motivated from physics. On one hand, comparing the distance equals velocity times time, and then using that to realize that signed area under the curve should be displacement, and on the other hand, realizing that displacement is just a difference of position. But the wonderful observation, mathematical observation, is that it works for any function you want to integrate. If you can find an antiderivative of that function, then you can use that function to calculate that integral. And so that allowed this concept, that allowed this material to have applications in many, many, many scientific areas like economics, medicine, engineering, not just physics. So for instance, if you want to do something like maybe you want to look at f of x equals cosine of x. And so you want to go from 0 to pi over 2. And so you want to look at the area under this curve from 0 to pi over 2, which means that you're calculating integral from 0 to pi over 2 cosine of x dx. Then you can evaluate this just by looking at sine pi over 2 minus sine of 0. Isn't that way better than trying to take a Riemann sum, than trying to take a limit of Riemann sums, so on and so forth? Sine of pi over 2, of course, equal to 1. Sine of 0, of course, equal to 0. So the area under this curve from 0 to pi over 2 is equal to 1. It's kind of a cool fact. Are there any questions or comments that I can answer for you? I do want to show you some idea of why this is true. I mean, we gave an example with f of x equals x, and then we saw that this integral was x squared over 2, and like we could calculate it. But why is it true for every single continuous function f that has an antiderivative? That's kind of more serious. Like, how could you prove that it's true for every single case, not just the example that we saw? And so the explanation of that actually ties together everything that we've really learned so far in the class. So it's really quite pretty. Fundamentally, what you want to show is that one side of an equality is equal to the other side. So what you do when you're trying to prove something like that is you just really start with one side of the equation, and you want to take you want to go step by step and demonstrate a chain of equalities where you can see each step, and finally arrive at your conclusion. And so what we want to do is convert f of b minus f of a into a Riemann sum for this integral, and then show that we can take the limit and nothing changes. And the way you can kind of do this is if you go from this interval from a to b, and you take any partition that you want, any partition that, it doesn't have to be uniform, but any partition, x naught, x1, xi, all the way up to xn, given any partition, I can now rewrite this f of b minus f of a as follows. So I could write something like f of x1 minus f of x0 plus f of x2 minus f of x1. Keep on going until I finally end up with f of xn minus f xn minus 1. So do you see why those two things are equal? You might first look at this and say, there's no way though that these two could be equal to each other because this has like so many terms, but this one doesn't. But look at what's happening. Minus f of x0, that's minus f of a. So this part is right there. Where's the x1? Well, the f of x1 cancels with this minus f of x1. The f of x2 cancels with the corresponding minus f of x2. So all those intermediate f of xi's will cancel in pairs, except for this one, because the sum stops here. There's no corresponding term that you're continuing to add. So there's nothing to cancel this. And this, of course, corresponds to f of b, because f of xn equals f of b. So that's what we call a telescoping sum when you get all those cancellations. Well, now what I want to do is I've got all of these intervals, 1, 2, 3, 4, 5, all the way up to n intervals. And I want to take each one of them in turn, and I want to use the mean value theorem on each interval in turn. So in other words, let's just focus on this first subinterval from x0 equals a all the way to x1. And I've got f of x1 minus f of x0. And if you remember what the mean value theorem says, it says that if you've got a function that's differentiable and whose derivative is continuous, then if you take the difference at the endpoints here, there has to be some point in the middle, and let's call it C1. I mean, it doesn't have to be right in the middle. There has to be some point inside this interval such that this difference is equal to capital F prime of C1 times x1 minus x0. I mean, the way we phrased it at that time was to say, if you look at the average rate of change of capital F on this interval, so if you divided both sides by x1 minus x0, the average rate of change of capital F, that would have to be equal to the instantaneous rate of change at some point inside the interval. And this is just a rewriting of that. But we also know that F prime of C1, that's just equal to little f of C1. That's the point. Capital F is an antiderivative of little f. So we're trying to integrate little f. We're trying to show that it's equal to capital F of B minus capital F of A. And the link between the antiderivative and the function is to say at each one of these subintervals, I can replace this difference with f of C1, for some C1 in the interval, I don't know which one, times delta x. So this is, of course, f of C1 times delta x1. And you can do that with the second interval, the third interval, the fourth interval. So like, I go ahead and replace this one with, what happens to this one? Well, you just do the same thing. You say, if you look now at the interval from x1 to x2, then there must be some point inside this interval, call it C2, such that the difference is equal to the derivative of capital F at the point C2 times x2 minus x1. So now just skip that one step and go ahead and rewrite this as f of C2 times delta x2. You keep on going and going and going. And this works for any partition that you picked. You could have picked just dividing it into equal subintervals, whatever you like. And then you recognize that this now is a Riemann sum. A Riemann sum for the function little f with the sample points given by C1 up to Cn and with the given partition. So you realize that f of b minus f of a is a Riemann sum for any partition you pick, and then sample points that you don't pick, but that's fine. And now what I'll do is I'll simply take a limit of both sides. So I'll take the limit I'm going to take a limit over all possible partitions, if you like, limit as the mesh of the partition goes to 0. But regardless of which partition you pick, the left-hand side stays the same. It stays f of b minus f of a. It doesn't matter which partition you pick, doesn't matter which sample points come out of it. So when you take the limit over all partitions on the left side, you still get f of b minus f of a. And then you recognize, of course, that this is just the definition of the integral. I mean, if this is a little opaque, then what you could do instead is simply pick the partition that uses delta xi equals delta x equals b minus a over n. And then you could substitute the middle step really with a limit as n goes to infinity. Like maybe k goes from 1 to n of f of ck delta x. I mean, at each step you have f of some sample point times delta x. And if it makes it intellectually easier to conceive of, instead of thinking of like a limit as the mesh of the partitions go to 0, you can pick these particular partitions and just take the limit as n goes to infinity. Of course, n going to infinity will make the mesh, the width of the partition, go to 0. So picking these special partitions is like a special case of that. But that's the argument. It shows that the integral is nothing but f of b minus f of a. And the intuitive way to do it is to chop this interval from a to b into bits and to use the mean value theorem on each little bit. And they'll add up to simply give you that integral. It's quite amazing that it works out so simply. Any questions or comments on that? So let's test our ability to work with this. I'm just going to pull a bunch of problems from the chapter exercises. And I haven't prepared anything in advance, but we'll just look at, and you can study this way too, just go to I'm in section 5.4, just go to the chapter exercises and see if you can do a bunch of the problems. So let's look at integral from 1 to 3. And the book writes it like this. The book writes dt over t squared. Don't be like the book. That's bad notation. Don't do that. Write like this. 1 over t squared dt. But if you see someone write like that, this is what they mean. So yeah, do that. Let's pick another one. Let's do integral from 0 to pi over 6 secant theta tangent theta d theta. Let's look at the integral from 0 to 3 of e to the 1 minus 6t dt. So I'll do the first one, and then I'll let all of you think about the second one and the third one before going over it. So you see this on the test, what are you going to do? I need to figure out an antiderivative of 1 over t squared, so that's going to be t to the minus 2. An antiderivative of that, remember your formula, you have n equals negative 2, and any derivative would just be t to the n plus 1 over n plus 1. And of course, you could add a constant to this, but any antiderivative will work. So why not just choose the constant that you add to be equal to 0? So I'm going to pick t to the minus 1 over minus 1. And then I'm going from 1 to 3. And of course, that's just rewriting that. That's minus 1 over t, going from 1 to 3. And so that's going to be plug in 3, and then minus 1 over 1. So that looks to me like the answer is 2/3. So I'm applying the fundamental theorem of calculus by calculating an antiderivative of the integrand, which I showed here. And then it's going to be f of b minus f of a, which I notated with the vertical line that I was telling you about, going from a to b. So here I substituted in the number 3 and then subtracted, substituting in the number 1, giving me 2/3 as my answer. So take a few moments. Can you do number 2 and number 3? So I'll put myself on mute, but chat me any questions or yell out any questions while you're working. Okay, so after letting you work for a few minutes, the trick to the second one, it would seem to me, is to find an antiderivative of secant theta times tangent theta. So that is to say, to find a function whose derivative is secant theta times tangent theta. So here's where your facility with taking derivatives will come in handy for you, because you'll need to know which function had derivative secant theta times tangent theta. So let me ask, if you want to put it in the chat, like, do you remember which trig function had derivative secant theta tangent theta? I'm hearing that we may not remember. If I recall correctly, we used the quotient rule to show that the derivative of tangent theta was secant theta times tangent theta. Right. Secant was 1 over cosine, this was sine over cosine, so you ended up with sine over cosine squared. Which would tell me that by the fundamental theorem of calculus, the integral of secant tangent from 0 to pi over 6 would be tangent theta evaluated from 0 to pi over 6. And so that's going to be tangent of pi over 6 minus tangent of 0. Tangent is sine over cosine, so tangent 0 is equal to 0. If you want to close this out, what's the exact answer going to be? You can plug it into your calculator for an approximation. Exactly what it is sine pi over 6 divided by cosine pi over 6. And so that's 30-degree angle. So sine is the shorter length, so that's sine 30 degrees is what? Is that 1/2? And cosine 30 degrees is root 3 over 2. Did I get that right, or did I get those reversed? I think that's right. And so this looks like the answer is 1 over root 3. What about this other one? You're going to be wanting to find an antiderivative for e raised to the power of 1 minus 16. And you know that the derivative of e to the t is e to the t. That much we've got. But what about something whose derivative is e to the 1 minus 6t? It seems to be a little bit more complicated. Remember the chain rule? Remember when we took derivative of e to the constant times t? The answer was something like k times e to the kt, because this was e to the kt times the derivative of the inside function, which is telling me that if I wanted to do something like, if I took the derivative of e to the 1 minus 6t, that would give me minus 6 times e to the 1 minus 6t, which basically solves the problem for me. Solves the problem for me because if you just divide by negative 6, then you'll get a function whose derivative is equal to e to the 1 minus 6t. So kind of like the takeaway message there is the thing that's multiplying t, if you divide by that, then that will give you the antiderivative. So this is going to become antiderivative, which is minus e to the 1 minus 6t over 6, going from 0 to 3. So plugging in 3, that gives us minus e to the 1 minus 18. And then minus is plus e to the 1 minus 0, so e to the 1, everything divided by 6. So this is like e minus e to the minus 17 over 6. It's not a great can't clean that up too much. So e to the minus 17 is 1 over e to the 17. I guess that's maybe the simplest way you can write it. So there's a question, why is it true that the derivative of e to the kt is k times e to the kt? That's because of the chain rule. So if you take a composition of two functions, you take the derivative, it's going to be derivative of the outside function, which is e to the f of t, times derivative of the inside function, which is f prime of t. In this case, for e to the kt, that's e to the kt times k. So the reason why that's true is due to the chain rule. Other questions, comments? Let's pull some more stuff from chapter exercises. This one is number 44 in the book. Integrate from 0 to 5. Absolute value of 3 minus x. I mean, I think you could do this two different ways. I think you could do this with geometry, and I think you could do this with fundamental theorem of calculus. If you do it with fundamental theorem of calculus, you're not going to have much luck finding an antiderivative of absolute value. But what you could do is you could break this up as a sum of two intervals where like each summand did not involve an absolute value, and then you could use the fundamental theorem of calculus. Chew on that for about 2 minutes. Can you draw the picture? Can you take the signed area from 0 to 5, get an answer? Can you also rewrite this integral, maybe from like 0 to 1 point, and then from that 1 point to 5? Can you rewrite it in such a way that there are no absolute values? And then can you use the fundamental theorem of calculus to do the integral and get the same answer? Work on that for a few minutes. Okay, after letting you work for a few moments, let's try to do it with geometry first. And the first thing I'll note, so what does this picture look like? So it's absolute value of 3 minus x, which is the same thing as absolute value of x minus 3, which would be the same thing as absolute value of x, and then translated over to the right by 3 units. So if I were to draw this picture, that's what this function looks like. And we're going from 0 to 5. So we're trying to do the sum of those two triangles. And when x is equal to 0, y is equal to 3, so this length has 3. When x is equal to 5, y is equal to 2. So this is a triangle with base equal to 3, height equal to 3. This one's a triangle with base equal to 2, height equal to 2. So the area of this one is 1/2 of base times height, so that's 9 over 2. And then this one would be 1/2 of base times height, so 4 over 2. So I'm getting 13/2 as my answer to that integral using geometry. Now, what about using the fundamental theorem of calculus and splitting it up in such a way that we no longer have an absolute value? Well, I think that this is the key to doing that. So I can rewrite this as integral from 0 to 3 plus integral from 3 to 5. And I'll just erase this part so I can keep working. So this is like the additivity of domain theorem that we talked about. Like if you're looking at the area under the curve, certainly you can reckon that as going from one place to the other and then taking the area and then going from the other place to the next one and then taking the signed area and adding them together. It's the same thing as the signed area for the whole integral. But the point is, if you look at 3 minus x, when x goes from 0 to 3, in that case, 3 minus x is going to be bigger than or equal to 0 no matter what, and therefore equal to 3 minus x without the absolute value. That's the benefit. So I can just write this as integral of 3 minus x. Whereas when x is bigger than 3, going from 3 to 5, then I've got 3 minus x. Then I've got 3 minus x being less than 0, less than or equal to 0. So the absolute value would be the negative of 3 minus x at that point. In other words, the absolute value would be equal to x minus 3. So I can rewrite this one as x minus 3. Now that I've rewritten it without the absolute values, it becomes quite straightforward to find an antiderivative. That's the point of doing that. There was no obvious candidate for an antiderivative of the absolute value of something, but there is an obvious candidate for like the absolute value for like 3 minus x or x minus 3. So in fact, the antiderivative of 3 minus x that I'll choose is just 3x minus x squared over 2, and I'll evaluate that from 0 to 3, and then I'm adding to this antiderivative of x minus 3, which will be x squared over 2 minus 3x. And this one I'll go from 3 to 5. Let's see if I get 13 halves out of that. So this one is 3 times x is 9 minus 9 halves. So plugging in 3, I get 9 minus 9 halves. Plugging in 0, I get 0. This one, plugging in 5, I get 25 over 2 minus 15. So I'm doing b minus a, so plugging in 5, 25 over 2 minus 15, and then subtract, plugging in 3, which gives me 9 halves minus 9. So if I add all those together and, well, yeah, let's add them together and see what we get. So 9 minus 9 halves is just 9 halves. What about this? 25 over 2 minus 15. So 15 is equal to 30 over 2. So shouldn't this be minus 5 over 2? 25 minus 30 over 2. And then I've got a minus 9 halves and a plus 9. And I've got 9 halves minus 9 halves. So I'm left with 9, which is the same as 18 over 2 minus 5 over 2, giving me 13 over 2. So giving me the same answer. It's kind of amazing the arithmetic worked out. I was sure I was going to make a mistake somewhere. So that's a selection of 5 problems chosen at random from the chapter exercises, illustrating how to use the fundamental theorem of calculus part 1. The other learning objective, we showed why the fundamental theorem of calculus part 1 is true. We gave some motivation comparing it to physics. And then the next class we'll do fundamental theorem of calculus part 2. So the part that we just did says that antiderivatives are useful for calculating integrals. The next part of the fundamental theorem of calculus guarantees for you that antiderivatives always exist no matter what. And I'll grade your tests this weekend and also turn them back to you. So thank you everybody for your time and attention. Have a great weekend. Please let me know any questions, comments, concerns, and take care.